Hello everyone, welcome to my YouTube channel. So today I'm going to solve the previous year question paper of TIFR GS. So I'll solve the question paper of 2019. I'll try to make a video for 2020, 21, 22, 23 as well. For TIFR GS 2024, I have already made 4 parts solution video. You can just go and check there. Okay, let's start. So the part A, it has 20 problems which is MCQ, and from in part B we have 20 problems which are mainly true and false, true false question. Okay, so the question number 1, the following sum of numbers expressed in decimal notation is equal to, this is clearly easy, you can just put some value for n and just check. This is just a easy problem, you can just do it within 2 minutes. So just take n equal to 1. What will you get? You get 10 square minus 10 minus 9 by 81, which is 1. That means the first one is correct. You can easily check that other options are not correct. Okay, what about the second one? Second one says that it asking about that xn is decreasing, increasing, constant, or oscillating, or anything. So xn plus 1 is minus 2 root n plus 1, and xn is 1 plus 1 by root 2 up to 1 by root n minus 2 root n. And clearly xn plus 1 minus xn will be 1 by root n plus 1 minus 2 root n plus 1 minus root n. This will be same as 1 by root n plus 1 minus 2 by root n plus 1 plus root n. Sorry, 2 by root n plus 1 plus root n. So you can easily check that 1 by root n plus 1 minus 2 by root n plus 1 plus root n is less than 0. Since because this is equal to 2 by 2 root n plus 1, and root n plus 1, 2 root n plus 1 is greater than root n plus 1 plus root n, because root n plus 1 is greater than root n. So this is less than 0. That means xn plus 1 minus xn is less than 0. That means in particular xn plus 1 is less than xn. That means it is decreasing. Okay. Now what about question number 3? Question number 3 says that it is given a function and then we have 4 statements. How many of the above statements are correct? Need to check that. Okay, so you can just easily check that limit x goes to 0 fx by x, which is equal to limit x goes to 0 x plus x square pi by x by x is 1. That means this statement is correct, that f dash 0 exists and is equal to 1. That means this is false. Okay, and you can see that I will ask you to plot this graph. This is a very important function. Why this is important? That since you may have some doubt that since f dash 0 is equal to 1, it is greater than 0, that means f is increasing in a neighborhood. Okay, f is increasing in a neighborhood of 0, which is absolutely wrong. This statement is wrong. There is different meaning of this f is increasing in a neighborhood. Okay, see, f dash 0 greater than equal to 1, which is greater than 0, this will imply that there exists a neighborhood of 0 such that fx is greater than f0. Okay, when x greater than 0, and fx is less than f0 when x less than 0 on some neighborhood. Okay, it says on some neighborhood, this is true. but it doesn't imply that whenever x greater than y, fx greater than fy. Okay, because this is true if f is increasing. F is increasing, then this is true, but this just says a comparison with f0, nothing else. Okay, that means in particular, say if you take say x1 x2 which is in that neighborhood and both are greater than 0, that from this you can just conclude that f of x1 greater than 0 and f of x2 greater than 0. That doesn't imply that x1 greater than x2 implies f of x1 greater than f of x2. Is it clear? Possibly I will make a different video for this particular problem, because this is a very important example and many students have some confusion regarding this. Okay, so the thing is that if at some point the derivative is greater than 0, means there exists some neighborhood on which if you pick any point, then the functional value will be greater than that value, and if you pick any point less than that, then functional value will be less than that. Okay, so here if f of x1 greater than 0, f of x2 greater than 0, that is fine. There is some neighborhood. In that neighborhood, if you pick x1 x2 greater than 0, this will, but this doesn't imply that this will hold. Okay, so f is not increasing in any neighborhood of 0. You can easily check by plotting this graph. Okay, you can see that in neighborhood of 0 this is oscillatory, and that is the because of the function cos, because this is oscillatory neighborhood of 0. Okay, cos pi by x. So that's why this is true, but this is false. So hence C is correct. Okay, now come to the fourth one. It is slightly tricky problem. Okay, this is slightly tricky problem and it takes time to clearly solve it, properly solve it. So if you put b equal to x plus y and a equal to x minus y, then you will get f of x plus y minus f of x minus y equal to 2y times f prime of x, right? This is just a functional equation. Okay, then if you derivative it with respect to x, then we will get this, right? And if you derivative this with respect to y, then you will get this plus this equal to this, and then if you add these two, what will you get? You will get okay. And f prime x minus y is minus y f prime x plus f prime x, if you just replace y by minus y. Okay, now if you differentiate it again with respect to x, you will get, sorry, if you differentiate it with respect to y, then we will get this one equal to f prime x. Okay, and if you differentiate this one with respect to y, you will get That means f double prime x plus y equal to f double prime x minus y. If you put x equal to y, then f double prime 2x equal to f double prime 0. That means f double prime, that means f double prime 2x is constant. That means in particular f double prime x is constant. That means f double prime is a constant. That means f is a polynomial of degree at most 2. Okay, this is correct. Okay, so now come to the problem number 5. Let's do it in a different page. So it says that rank t less equal to rank of t cube. Then we need to check the condition between null space and range space. It is a very known problem and easy problem. Okay, so see, rank t less equal to rank t cube, and we always know that, and this is always true, that rank t cube is less equal to rank t, because if you make bigger the power, then rank is definitely less than this. This is true, easy fact. Then from these two part, you can say that rank of t equal to rank of t cube, and again rank of t square is in between rank of t and rank of t cube. Then it will imply that rank of t square equal to rank of t, right? Okay, then nullity of t square equal to nullity of t. We know that null space of t is contained in null space of t square. It is easy because if x belongs to null space of t, that means tx equal to 0. That means t square x is also 0. So x is in null space of t square. And nullity of t square equal to nullity of t. That will imply that dimension of, sorry, that will imply directly that these two are equal. These two are equal, right? Okay, these two are equal. Now let x belongs to nt intersection rt. That means tx equal to 0. Why these two are equal? Because if a subspace has the same dimension with this vector space itself, that means they are equal, right? Because their dimension is same. Nullity of t square means equal to nullity of t means dimension of nt equal to dimension of nt square, and one is inside another one, and it is subspace of this, and both have same dimension. That means they are equal. So if tx equal to 0 and there exists y belongs to v such that ty equal to x, then t square y equal to tx equal to 0. That means y belongs to nt square, which is same equal to nt. That means ty equal to 0, and ty equal to x. That means x equal to 0. So intersection is trivial. That means nt intersection rt singleton. Okay. This one is correct. Problem number 6. The limit n goes to infinity n square 0 to 1 by 1 plus x squared power n dx. It's a technical problem. It's not so straightforward. Say, So you know e power x square is greater than 1 plus x square from the expansion of e power x square. Then e power n x square is greater than 1 plus x square power n. Power n 0 to 1 dx, right? And this is greater than 0 to n square x by e power n x square dx. Okay, now take this integral 0 to 1 n square x by e power n x square dx. 0 to n by 2 dz by e power z by taking z equal to nx square. One by n. So these diverges to infinity because the second part goes to 0 but first part goes to infinity. So by sandwich theorem, not sandwich, like you can just one-sided inequality, but you can just you can just see that limit n is to infinity 0 to 1 n square 1 plus x square n dx is to infinity, right? Oh, it is when some mistake is there, technical mistake, sorry for this. So okay, it is some technical mistake is there. Some of the previous solution is already gone. By the way, this the solution is like this is done, 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 this is also done. This is a easy fact. Okay, you can just do it by 2 by 2 matrix, that rank of A transpose equal to rank of A. Okay, if A is real matrix, but for complex it is not true, but for complex it is not true. So in particular, if I want to prove it, the proof is very lengthy. Okay, so maybe I will make a separate video. If you want, just comment below. Okay, but this is a general fact, so but it takes time to explain, so I don't want to explain it because otherwise video becomes very lengthy. Okay, okay, but you can easily find the counter example. Okay, if you need, you can just comment below so that I will make a different video. Problem number 8, this is application of Stone-Wester's theorem. Okay, so I have already discussed in many videos about Wester's approximation theorem. Stone-Wester's theorem is a general version of this. Okay, so if you know Stone-Wester's theorem, then you can apply it everywhere. So I will make a different video particularly for Stone-Wester's theorem, and then I will make an application as this problem. This problem will be the application of that Stone-Wester's theorem in that video. Okay, I'll make a different video for this, but you can just search in Google and you will get idea how to solve this. Okay, this application of Stone-Wester's theorem. Okay, this one is also a easy one. So fx equal to Sin x cube by x. Okay, so this problem is for you. See, if I want to solve all the problems, the video will be very lengthy. But this one is easy one, because this is, you can just easily check this is bounded. First of all, if so this one is less than 1 by x, right? So if x is greater than 1, then it is clearly bounded, there is no problem. But in case of x is less than 1, you can just take this one. So sin x cube by x, limit x tends to 0, this is same as sin x cube by x cube times x square, right? So limit x tends to 0, this is 0, right? This is 0. So on closed bounded intervals is 0. It is defined on f0 to infinity, but I can define at f0 to be 0 itself. Okay, I can define f0 to be 0 itself. So on a closed bounded intervals is 0 to 1, this is already bounded, because that is a compact set and it's a continuous function on that. So that means it must be bounded there. Okay, and for x greater than 1, it's already bounded. Okay, and uniformly continuous thing is also easy to check. Okay, you can just do it by definition also. Let fx minus mod fx minus fy less than epsilon. When you can choose fix an epsilon and you can choose a delta depending on epsilon, only depending on epsilon, not depending on any point x, such that this is just a computational problem. Okay, okay. Now question number 10. X is equal to x belongs to R such that x equal to trace a for some a belongs to M4R such that a square equal to a. See, a square equal to a means x square minus x equal to 0 is an annihilating polynomial. That means minimal polynomial of a must divide x square minus x. That means possible eigenvalue is 0 and 1. Right. Now if all the eigenvalues are 0 and trace is sum of eigenvalues, and this is a M4R, so that means 4 eigenvalues are there. Maybe 4 are same, maybe 4 are different. I mean, not 4 are different, this is not possible because only possible eigenvalues are 0 and 1. So the thing is that if all the eigenvalues are 1, you will get 4. If exactly 3 is 1 and 1 is 0, you will get 3, 2, 1 and 0. So the possible a, so the ace is just this. Okay, question number 11. This is a very important problem. Okay, very important problem. uh, Many times it is asked in interview in different exam like NBHM. It is also asked in TIFR, and as well as it is asked in GATE also. Okay, I have already made this video. I have already made this separate video for particular problem. You can just go my playlist section, and there you should go to interesting problem, that section. Then you will find this interesting problem. Then you will find this is already solved there. Okay, so it should be a sequence of function from R to R defined by fnx equal to 1 by n e power n minus n square x square. Okay, so fnx is 1 by n e power n square x square. You can easily check that the limit function f equal to 0. Okay, then mn equal to supremum. You don't need mn because you can directly do that. Fnx minus fx that is mod 1 by n e power n square x square, which is less than 1 by n, right? So that means for any given epsilon, greater than 0, choose n such that 1 by n less than epsilon, that mod fnx minus fx less than epsilon for all n and for all x. That's why it is uniformly convergent. Okay. So that means option C is not correct. Okay. Option B is not correct. What about option D? What is derivative? Minus 2nx by e power n square x square. So fn prime 1 by n is minus 2 by e, right? So you can easily check that fn prime of x also goes to, say, uniformly converge, pointwise converges to f, not f, I should take it c is equal to 0. I mean, it pointwise converges to 0 function, right? Now if we define mn, say supremum of, say, minus a comma a, because it is, say, take an interval containing origin, then fn prime x minus gx, that is greater or equal to fn prime of 1 by n, which is minus mod fn prime by 1 by n, which is mod 1, which is 2 by e. So that means mn doesn't converge to 0, right? So mn doesn't converge to 0, hence fn prime is not uniformly convergent, okay, on any interval containing origin. Means D is correct. Okay. Now question number 30. This is also an easy one. Okay, just show that, you can just inductively show that. Okay, two step, inductively show that, first you can easily check that root 2 power root 2 is less than, sorry, root 2 power root 2 is greater than show root 2 is greater than root 2 power 1, because root 2 is greater than 1, right? That means x2 is greater than x1. Then assume that xn is greater than xn minus 1, then you can easily show that xn plus 1 is greater than xn. So that means xn is monotonically increasing. And by monotone convergence theorem, what you need to show? If it is monotonically increasing and bounded above, then it is convergent, and then you can find the limit, right? So it is monotonically increasing and it is bounded above by 2, because see, x1 is strictly less than 2. Okay, you can assume that xn less than 2, then xn plus 1 will be root 2 power xn, which is less than root 2 power 2, which is 2. That means it is bounded above by 2. So by monotone convergence theorem, it is convergent and limit is precisely 2. That comes from this relation. So this one is correct. This one is easy one. Okay, come to the problem number 14. Problem number 14. So take first C, this is 4 3 2 1. So that means you can just easily take this function mod x. Clearly this satisfies this condition, but this is not differentiable, so first option is clearly wrong. Okay, now if you read option C, it is extremely hard to find such a function, if this is true or not. You don't know it is true or not, but even if that option is true, it is extremely hard to find such a function in exam hall. at least for me, definitely. So that's why in this case you can just, since it is MCQ, so you can just try to discard it because you don't have any other option to find this, so you can just try to discard it. But that you can do, as you can see that mod fx minus f0 is less equal to 4321 mod x minus 0, which implies, I think I should go to different page. So we have already mod fx minus fy is less equal to 4321 mod x minus y. So fx minus f0 less equal to 4321 mod x, means mod fx is less equal to mod f0 plus 4321 mod x, means is less equal to f0 mod x plus 4321. Because if you find the limit x goes to plus infinity or negative infinity, anything, mod fx minus this is at least bounded above by 4321. Right, so that means option B is false. Clearly option B is false because it says that fx minus mod f goes to infinity, which is not possible, as well as true for negative infinity also. You can just check. And so what about the fourth option? Fourth option says that it is not possible to find a sequence xn of real number such that limit n tends to infinity xn is infinity, but uh, it is not possible, but it is always possible from the definition, right? Because mod f of xn by xn is less equal to mod f0 by xn plus 4321. If you take any xn which goes to infinity, then this part will vanish, this part goes to 0, and this will less equal to 4321, which is strictly less than 10,000. So that means it is always possible to find. Hence this option is also wrong, so this is correct. Okay, so this time there are lot of question coming from uniform converges and so on, but most of the questions are easy. So okay, question number 15. Question number 15 says that fn be a sequence of function from R to R defined by fnx equal to root over 1 plus nx square n. Okay, so first see that fnx equal to root over 1 plus nx square divided by 1 plus n square, which is 1 by n square plus x square. That means that goes to x, root over x square, which is mod x. Okay, now fnx converges uniformly on R. How can I show that? Fnx, okay, I think some issue is there. Okay, so fnx is root over 1 plus nx square by n, right? So mod fnx minus fx, which is mod 1 plus n square x square by n minus n times mod x by n. Plus n square x square minus this, which is less equal to 1 by n, 1 by root over 1 plus n square x square plus mod x, which is less equal to 1 by n, because this is always greater than 1. So that means 1 by this is less than n. So that means it is independent of x. So only depends on epsilon. So you can just take for any given epsilon, you can choose some n such that 1 by n less than epsilon, and then fnx minus fx mod, that is less than epsilon for any n and any x. So that means fn is uniformly convergent to f. Now if fn prime is uniformly converges to some function g, that means g has to be equal to f prime. By definitely, right? It has to be equal to f prime, but f is mod x. F is itself is not differentiable. That's why fn prime cannot converge uniformly to any function. Okay. Hence, fn converges uniformly on R, but fn prime doesn't. So this is correct. Okay. Question number 16. So this is zxy to f2x modulo x cube plus x squared plus x plus 1, which is same as a0 bar plus a1, sorry, a0 plus a1 x bar plus a2 x bar square, where ai belongs to f2. Okay. See, if you want to define a ring homomorphism from this, if you know the value of x and y under the homomorphism, then you will get a value of everything, because since it is ring homomorphism, 1 must go to 1, so you know where z, any integer goes. Okay, and if you know that where x goes and y goes, you will know that where the every element goes. Okay, so kind of x and y are some kind of basis element. Okay, now how many elements are there? 2 2 2, that means 8 elements. This cardinality is 8 elements, right? So and now you can define x to be anywhere. X goes to some anything here, some f, and y goes to some g, and in this way you can just extend any polynomial in z variable, say hxy goes to some in polynomial of fc inside it. So this is enough to define x to be anything. That means for x you have 8 choice, for y you have 8 choice. That means total you have choice 64 is 2 to power 6. So one is easy. Okay. Okay. Question number 17 is a very known example. Okay. If you have read metric space, connectedness, path connectedness, then definitely you will encounter this example. So just search Google by topologist sine curve. Okay, and we will get enough information. I don't want to waste time. Okay, question number 18 is a very nice problem, but I need to explain it in very detail, so that I will make a separate video for this. Okay, it's a very important problem. I will make a separate video for this. Okay, question number 19. Question number 19 is, so this is clearly a linear map, right? So f goes to f plus df dx. This is a linear map. There is no problem. That means if you want to check the injectivity, you can just solve this ODE. Okay, and by solving this ODE, what will you get? Yeah, so that means you will get f equal to e power c minus x, where c is some constant. So in particular, if you choose f equal to e power 1 minus x and g equal to e power minus x, both goes to 0, but they are different functions, so injectivity doesn't hold. But surjectivity follows from the existence of solution from ODE, that if you have c infinity function, You have C infinity function, right? That means you will always find a solution of this ODE, this linear ODE. Always find a solution of this. This is the existence of solution. This comes from the existence of solution. Hence, surjective but not injective. Okay. Question number 20 is from probability question. It's part of a uh, general general section. So a stick of length 1 is broken into two pieces, cutting at a randomly chosen point. What is the expected length of smaller pieces? See, the length of smaller pieces always vary from 0 to half, right? Always vary from, because this is the smaller pieces, right? That means you need to take an average of this, because this is a continuous process, so it can take any value in between 0 to half, right? So this is a so that's why you need, here space is continuous, so you need to find the average. So how can you find that? You can just integrate is x dx by this length. This length is 2, means 2 times x square by 2 half 0, it means 1 by 4. This is correct. Okay, now come to the part B. So there exists a continuous function f from R to R such that f of q equal to f of q is contained in R minus q, f of R minus q is contained in q. F of, right, so f of q is contained in R minus q, right? See, q is countable, that means f of q is also countable, right? And f of R minus q is also countable, because it is already inside q. That means f of R is countable, and f is continuous. An image of a continuous function must be an interval, right? Image of continuous function in R must be an interval. But if it is any non-trivial interval, then then it will be uncountable. That means this must have to be constant. But since f of q is in, f of any rational number is a irrational number, f of any irrational number is a rational number, it cannot be constant. Hence, there doesn't exist such a continuous function. So this is false. Problem number 2, I can just easily explain that a belongs to M10R, a square plus a plus I is 0. That means a square plus a plus I is an annihilating polynomial for a. So minimal polynomial must divide it, right? Minimal polynomial must divide it, right? But since it is M10R, that means minimal polynomial must have must be a square plus a plus identity. I mean, minimal polynomial is x square plus x plus 1. And if a is not invertible, that means 0 is an eigenvalue, right? That means 0 must be a root of the minimal polynomial. But x square plus x plus 1 doesn't have 0 as its root. So that's why it is clearly 0 is not an eigenvalue, so a is invertible. Now, the problem number 3, x is subset of q2. Suppose that each continuous function f from x to R2 is bounded, then x is necessarily finite. Okay, this is the question. See, you have continuous function x to R2 which is bounded, right? Then it claims that x is necessarily finite, which is a very strong. So most of the cases it should not be true. But when a function, if you specify a particular domain, what kind of special domain if you specify, then always image of any continuous function is bounded in R2. If you specify it as a compact set. So if X is compact, then image must be compact, because continuous image of a compact set. If X is compact, that means Fx is compact, and that will imply Fx is bounded in R2, because compact implies bounded in R2, right? Closed and bounded in R2. So it is bounded in R2. So that means if you choose any compact set, right? If you choose any compact set, then we are done. Then choose any compact set in Q2, which is not finite. Then we are done. Okay. You can just particularly choose, say, 1 by n, or 0 comma 1 by n union 0 0, this closed set, that you can also choose. This is, you can just choose anything which is infinite compact set here. Then we are done. Okay, problem number 4 is very interesting and fine. A is a 2 by 2 complex matrix, is invertible and diagonalizable, such that A and A square has same characteristic polynomial. Then A is 2 by 2 identity matrix. See, if A and A square has same characteristic polynomial, then A and A square both have same eigenvalue. So let eigenvalue of A is, say, lambda and lambda prime. That may not be equal. Okay, that may not be equal, or may be equal. I just denote it lambda and lambda prime. Then lambda and lambda prime are eigenvalue of A square also. Again, if lambda and lambda prime are eigenvalue of A, that means lambda square and lambda prime square are eigenvalue of A square also. Now most of the students did the same mistake, that after that they are assuming that lambda square equal to lambda and lambda prime square equal to lambda prime. But that may not be true. It may happen that lambda prime square is lambda and lambda square is lambda prime. That may be true, but this is small checking. Okay, so if this thing is happen, okay, suppose this thing happens, then what will you get? You will get lambda power 4 is lambda, right? And it is given that A is invertible. That means 0 cannot be an eigenvalue. That means lambda cube is equal to 1, right? That means lambda is 1 omega omega square. So let's take lambda to be omega and lambda prime to be omega square. Square. This is a complex matrix. What about it? It is A. A square is A and A square both have same characteristic polynomial. They are diagonalizable clearly, but A is not identity matrix. Right? Okay. Problem number 5. This is an easy one. Just use the inequality for rank of 2 matrix AB, and then do for 3 matrix. Okay, or you can directly use the formula for 3 matrix. Is not an important question, so you can just do it. Problem number 6 is very interesting. Problem number 6 says that for any n greater or equal to 2, there exists a real matrix A such that A power p greater or equal to 1 spans R vectors per M and R. So dimension of M and R over R is n square, right? So if choose, and now if you choose any matrix, that means minimal polynomial has degree at most n, right? That means A power n is span of 1a square up to A power n minus 1. In particular, A power p belongs to span of 1a square A power n minus 1 for any p greater or equal to n. So that means in particular, if you take this spanning set for any A, if you take the set A power p and take its spans, then dimension is at most n. Dimension is at most n, because it is always lies in the span of 1 to A power n minus 1. So dimension is at most n. But if it spans MNR, then dimension must be n square, which is not possible, because n is at least 2 here. N is at least 2 here. So it's not possible. N is strictly less than n square. Okay. That means this is false. Okay. Question number 7. The matrices, these are this. So two matrices similar if and only if they are Jordan form. Okay. You need to know Jordan canonical form. Jordan canonical form is same. Same. Just find the Jordan canonical form of this. You can just easily see that all the eigenvalues, this is a triangular matrix, so all upper triangular and second one is a lower triangular, so diagonal matrix, so upper triangular matrix and lower triangular matrix, so eigenvalues are 0 itself. Okay, and both have rank 2, that means nullity is 1, that means it has exactly one 3 by 3 Jordan block, right? Both have exactly one 3 by 3 Jordan block, so that means their Jordan canonical form is same, so they are similar. So now come to the problem number 8. Consider the set A in M3R 3 by 3 real matrices with characteristic polynomial x cube minus 3x square plus 2x minus 1. Then A is a compact subset of M3R. Okay, M3R. See, this is, so x cube minus 3x square plus 2x minus 1. You can just check the root. You can just check the root. Okay, so see, x cube minus 3x square plus x cube minus 3x square x cube minus 3x square plus 2x minus 1. So at least one real solution is there, right? So that means this matrix, if you take any matrix whose characteristic polynomial like this, then at least one real eigenvalue exists. So they let lambda is a real eigenvalue, and I'm not interested about other eigenvalues. Say this is A and B. Okay, other eigenvalues are this. So if you take this, so say if you divide the x cube minus 3x square plus 2x minus 1 by x minus lambda, you will get that x minus lambda times, say, some x square plus ax plus b. Okay, I'm assuming. Okay, so let me write it properly. So I have x cube minus 3x square plus 2x minus 1 equal to 0. So let lambda be real solution of this. That means this is real eigenvalue, and it must have other two real eigenvalue or may not. I'm not interested. Okay, so then what you can do, you can write x cube minus 3x square plus 2x minus 1 as x minus lambda times x square plus ax plus b. Now take this matrix lambda, say if I draw that, n 0 0 0, and here is a block such that the characteristic polynomial for this block is x square plus ax plus b, and n is any natural number. Then you can say this is an. Then you can check that characteristic polynomial for A is this one, right? Characteristic polynomial for A is this one, but I am taking n here. You can take any n. So when you are thinking M3R as R9, that means one component is already unbounded, so it cannot be compact set, right? It's already unbounded, so it cannot be compact, because compact implies bounded, right? So that means this is false. This is not compact. Okay. So there exists an injective ring homomorphism from product ring to CR with set of all continuous function. So product ring say R cross R to CR, right? Take 1, 0. That must go to some f, where f square equal to f, right? It is injective. So and f square equal to f, right? And since f is continuous, then f equal to 0 or f is identically 1, right? Because f is continuous and f square equal to f, right? But 1, 0 goes to f, here 0, 1 must go to some g, 1, 1 must go to some h. All these three are idempotent elements, so it must go to some idempotent elements. So here we have already 4 idempotent elements, but here is exactly 2. So that's why there cannot be a injective ring homomorphism, because it has already 4 idempotent elements, so it must map to at least 4 idempotent elements must be there in CR, but that is not true. Hence, this is false. R and R direct sum R is isomorphic as vector space over Q. That is true, right? Because dimension of R over Q and dimension of R plus R over Q both are same. We know that two vector spaces are isomorphic over some field F if and only if their dimension is same. Because if their dimension are same, that means you have a bijection between the basis element, and if you define a bijection from a basis element to this, that will uniquely extend to a linear map, which is an isomorphism, because on the basis element this is already a bijection, right? So that gives you an isomorphism. Hence, since dimension over Q, dimension of R over Q and dimension of R plus R over Q both are same, that's why this is isomorphic. Okay, question number 11 I will solve. Okay, but before going to solve 11, let me solve the others. Let me solve first the easy ones. So the idempotent elements in Z51 is 0 and 1 only. So idempotent means what? Idempotent means x square equal to x in Z51. That means 51 must divide x into x minus 1. Right. So let's take x to be 18. Then 51 must divide 18 times 17. Right. That means 18 is also an idempotent element in Z51. So that means this is false. Okay. So technical issue is there. Okay. Okay, that means question number 11 left. I'll do 13 also. Before going to do that, let me solve the other ones, because that seems okay. The ring Rx mod x power 5 plus x minus 3 is an integral domain, right? That means x power 5 plus x minus 3, this ideal is a prime ideal. But we know that over R, any polynomial of degree greater or equal to 3 is reducible. So you can reduce it. That will imply that x cube plus x minus 3 is a reducible polynomial. Hence, this question cannot be an integral. The same question comes in 2023 also. The easy one. Okay. This cannot be, because any polynomial of degree greater or equal to 3 must be irreducible. In particular, since it is x, it has a root, right? It has a root. You can easily check. It has a root because it is an odd degree polynomial, so it has a root. That means this cannot be an integral domain, because you can take x minus that root times gx, and then their product is in here x, but x minus this and that is not here. So x power 5 plus x minus 3, this ideal is not a prime ideal, so the quotient is not an integral domain. Okay. Question number 50 is a very standard problem that given a group, there is a converse of Lagrange theorem, which is not true, and group of order 12, we know the very known group, that is A4. A4 doesn't have any subgroup of order 6. That's why problem 15, question number 15 is also false. Question number 16. Question number 16 is some technical issue is there. Lot of technical issues is there. I don't want to, because right. So H and N are subgroup of G such that N is normal subgroup of G. Order of G mod N and H are relatively prime, then H is necessarily contained in N. You just define G to Z mod N, the natural projection map, okay, and take the image of H. This is F, right? So order of f of H must divides order of H, and order of f of H must divide order of G mod N. Since order of H and order of G mod N relatively prime, that means order of f of H is 1. That means f of H is contained in kernel of F, and kernel of F is precisely N. Sorry, H is contained in kernel of F, because f of H, order of f of H is 1. That means any element goes to the identity element here. So that means H is contained in kernel of F. That means H is contained in N. Okay. If every proper subgroup of an infinite group G is cyclic, then G is cyclic or not. An example of this thing is that multiplicative group of complex number to 1. Okay. Okay. So define Hn is 1. You can show that Hn is contained in Hn plus 1, and Hn is cyclic. Okay, Hn is cyclic. You can first show that Hn is cyclic. Hn is contained in Hn plus 1. Okay, and you need to show that G is non-cyclic. Okay, I hope you can do this, or I should properly mention that you can see that Hn is cyclic. That is easy, and Hn is contained in Hn plus 1. That is also easy, because if x belongs to Hn, that means x power 2 power n is 1. That means x power 2 power n plus 1, that is also 1, right? Because x power 2 power n whole square, that is 1. So that means x power 2 power n plus 1 is 1, so that is inside this. So Hn is cyclic, and you need to show that all the subgroups are precisely in this form, of this form Hn. Then you are done. Okay, so I'll make a separate video for this, because this seems to be a very interesting problem. Okay, I'll make a separate video for this if you need. Then each solution of the differential equation y double prime plus e power x y equal to 0 remains bounded. This is true or false? I don't have extra pages there. Okay, so let me explain. Observe this: y double prime plus e to the power x y equal to 0. So if y is positive, if it is not bounded, okay, so if y is positive for very large x, okay, if y is positive, that means e power x times y, that is also positive. Then since this equation holds, that means if yx greater than 0, that will imply that y double prime x is less than 0. That, so what that means, it's kind of concave, so that means it is always bounded. That is true for negative x also, that if x goes to negative infinity, then, and if yx is negative, okay, not negative infinity, even x goes to positive infinity, and if yx is negative, then e power x times yx is negative, then y double prime is positive, right? Then also it is kind of this, or it is kind of this, that means this is bounded. Okay, this is the geometric intuition. But if you want to solve it properly, I don't know, maybe some ODE expert can do this. I'm not expert. I don't know what is the exact solution of this ODE looks like. If you can solve that, then you can argue it very properly. But geometrically or intuitively, you can see that this is true statement. This remains bounded. Okay. Now question number 20. Question number 20 says that v from R to R2, we have C infinity function. There exists a t naught belongs to 0 1 such that v1 minus v0 is a scalar multiple of this. Okay, and okay, so how many questions I leave? Question number 19. So I will make a separate video for particularly these problems. Okay, that will be uploaded within 2 days, no problem. So let me do that 20, because it is already becomes a very lengthy video. So v R2 we have C infinity function, then there exists a t naught such that v1 minus v0 is scalar multiple of this. So let vt equal to ft gt. Okay, so here it is saying that f prime t naught g prime t naught should be equal to f of 1 minus f of 0 g of 1 minus g of 0. So I am trying to do some technique. Okay, see, so g of 1 minus g of 0 equal to lambda times g prime of t naught. So let's take a first let's take a function g. Okay, let's if you can find any different solution, easy solution, please tell me. Okay, my solution is slightly complicated. So let's take a g such that g of 1 minus g of 0 is 0, and there exists exactly one point such that g prime vanishes. Okay, there exists exactly one point such that g prime is vanishes. Okay, so in particular, easily I can take the symmetric function with respect to half, which is say kind of this function x minus half square. Then clearly gx is x minus half square. Okay, this is say gx x minus half square. That means g of 1 minus g of 0 is 0. That means lambda times g of t naught must be 0. So either lambda is 0 or t naught must be half, because z prime t naught 0 means t naught has to be half. So either lambda equal to 0 or t naught equal to half, right? Now choose f to be any function, such that f of 1 minus f of 0 is non-zero and f prime half is 0. Choose any function. This kind of function you can easily choose, right? Because geometrically what you have to do, say you just, this is say half, this is say 1, this is say 0. You can take some function like this, say this. Okay, some function like this. I will not give an example, please try to think and comment. Kind of function, any function such as f of 1 minus f of 0 is non-zero, but f prime half is 0. Then by given condition, f1 minus f0 must be lambda times f prime t naught. So if lambda equal to 0, then this must be 0, but this is non-zero, which is a contradiction. Or if lambda not equal to 0, that means t not equal to half, but f prime t naught is also 0. So this part is always 0, but this part is always non-zero. So this is not true. Okay, that means if I choose v to be in such a way where f is a c infinity or f is c infinity function, you can just do that. Okay, slightly, because we have already x minus half square is kind of this. I just down it slightly and make it, or you can do it in different way also. This is a clearly a false statement. Okay, okay, so only thing I am left 19, 17, 13, 11, 19, 17, 13, 11, right? And question number 8. Okay, so only 5 problems are left. Only 5 problems are left. I'll make a separate video for this. Okay, thank you.